So our next talk will be by Mikkel here, and on applications of module theory to databases. Take it away.
Thank you. So let me start with a little teaser. So a triangle query is it's a query where we try to find 3 points in a graph that are all connected like a tree cycle. And as an example, let's take the Wikipedia database, and let's say that there's a link between A and B if A has a reference to B, like a link. And then let's try to execute this query in MySQL. And let's suppose that we have sort of done a reasonable job of optimizing the query, and we've made our indices and so on. How long does it take? For this particular example, it takes almost 2 hours to get an answer. Now, what happens if we code up a Haskell function using some fancy algebra, but otherwise just a 3-liner, basically? It takes about 10 minutes to write. It takes about 4 seconds to execute. So how is this simple Haskell function? It's clearly asymptotically better than the MySQL execution, and it's clearly a lot simpler. So how does this happen? Well, the general strategy that we're using in this approach is, well, take something like query processing and then forget all we learned in the freshman course, like forget relational algebra, forget SQL. Let's use algebra instead. Let's use module theory, linear algebra, that kind of stuff. Then we take a dose of category theory and sprinkle on top, and then, a few days later we get results. We can recover previous results like factorized databases, and we can generate new results like efficient algorithms for query evaluation. We can get efficient data representations beyond what has been seen already. And so that's the general approach that we've been using in this work to try to combine sort of algebra with query processing. Okay, so let's get some basics out of the way. A module is it's basically an abelian group and a ring, and the ring is acting on the group. So we have set, and we have addition of elements, and we have scalar multiplication. And then they obey all the laws that you would want it to obey, including commutativity, which is important. And then given this algebraic structure, we can of course have maps that preserve the structure, which in this case is linear maps, or homomorphisms. And additionally, we want to consider the idea of bilinear maps, which is just, well, what if we have 2 different modules, well, a pair of modules, and we want to map out of them? Well, then we want something that is linear in each argument separately, and that's what we're going to call a bilinear map. And this the structure of modules and linear maps forms a category, should be well known. And so let's look at the inhabitants of this category. We have the trivial module, sometimes just called the zero module. Consists of a single element, just a 0. That is the ring itself, here called K because we're sort of thinking a bit about linear algebra, so K is a field sometimes, but in general it can be any ring. So that forms a module, and then for any 2 modules we can form the module consisting of linear maps with pointwise operations. Okay, so with the formalities out of the way, let's look at some of the more interesting constructions. The first one of which is coproducts. So the coproduct, so the general property works like this, which should be familiar, that we have some family of injections, and then for any other module with a family of injections, we have a unique map out of the coproduct, which would denote with case because it's essentially case analysis. And well, the thing is in the category of modules, co-products and products kind of coincide in the finite case, but we're not going to talk much about products here. But the co-product it's not quite, if you're used to thinking about co-products in the set theory or the category of sets or types, it's a little bit different here because of the additive structure. But we'll get to that. And then the particular case of with arity 2, well, that's just a binary co-product, which we call it a direct sum. So we have this kind of handy notation for just adding two things of different types. Now here's where it gets interesting. So if we look at this in the most abstract setting, which is just a category with, a category of modules, but it can be even more general than that, but let's just look at modules. We can prove the following natural isomorphisms. That if we have the co-product of the empty set, well, that's the trivial module, and the co-product of the unit set is just the ring. And then sums of sets become direct sums of modules, and product of sets become iterated modules. So with this, we actually have a representation for all polynomials of sets, right? So and we can do, I haven't shown this here, but we can do fixed points as well. So essentially, we can take any algebraic data type and then generate the co-product over that, and via these natural isomorphisms, we can decompose it into iterations, direct sums, and the primitives here. And what this turns out to be is actually the structure of generic tries, as in the thing that you code up in Haskell using type classes and associated data families and that kind of stuff. This is the exact same thing that we get just by looking at category theory and natural isomorphisms. Right, so let's look at a particular case of a co-product, a very useful case. So let's just, for convenience, fix the ring to be integers. And then let's look at a co-product, which is just a bunch of copies of the integers. So it's just a homogeneous co-product with b copies of the integers. And then the specialized property looks like this. So we can map out of this module just by specifying what happens to each element. And this we're going to call polysets. So there's a functor here that takes a set into a module, and we call that the polyset over that given set. So what does this mean in practical terms? Well, so the elements of polysets are finite sets. So we have a polyset consists of a finite number of elements, each with a multiplicity. This is how you would denote that in like existing multiset developments. But using annotation, well, that's just the linear combination. So we're using the introduction rule for each element to make it into an element of the module, and then we just multiply, right? So it's just we're just using the notation of a module to construct elements. So we don't necessarily need to write it in this canonical form. We can just use any kind of expression in the language of modules to write down elements, but this one in particular would be like the standard canonical choice. And well, to map out, we can just, like as we usually do in algebra, we just, f is defined by its action on each of the basis elements. So the other important concept that we're going to look at is tensor products. So we can present this as a universal property as well. So the tensor product is equipped with a bilinear operator. So this is a bilinear operation from u cross v into u tensor v. And then the property is that, well, given any bilinear map, we can mediate between them by this operation, which I call uncurry. So basically it means that any bilinear map can be represented as a map out of the tensor product like this. So we don't really need to consider bilinear maps as such when we have the tensor product. We can just consider linear maps out of the tensor product. But given this tensor product construction, we have a very powerful notation, which is that, well, we can just take any elements, an element from U and an element from V, and then we can just combine them using this tensor product notation. Now, this might not seem like much, but the thing is that these elements in themselves can be any kind of expression. So we can take a big sum of a number of elements, and both of them can be complicated sums, and then we just tensor them together using this tensor constructor. Now, the important thing is that we don't multiply out. So the tensor product comes with a bunch of properties like linearity in both arguments. So we could choose to say, well, let's normalize this and multiply out the sums, but that incurs a quadratic blow-up in the worst case. So we're not going to do that. We're specifically going to delay this kind of canonicalization of the tensor product for as long as possible. In particular, if at some point we map out of the tensor product, well, then we can just apply the function to each argument separately. And if we didn't map out in the first case, well, we're never going to, supposing that this function that's mapping out doesn't really care. Now, remember the tensor products are not quite the products that are not like Cartesian products in the sense that you can't just write a projection in general. Like there's no non-zero natural map that goes from U tensor V to U, because then you're throwing away information from V. There's a multiplicity in V that we're forgetting. But if the thing that we're throwing away is, for instance, a polyset, then it is possible because polysets can be counted, right? We can say, like, what is, well, in terms of linear algebra, we would say, well, it has a basis, right? But we don't really think in terms of basis. We just think, well, this is the polyset generated by this set, and therefore we can forget it in an ordered sort of coherent way, right? And then, well, we have a factorial action, so we can just take the tensor product of two functions and, well, acts on them separately. Okay, so with all that, you might be wondering, well, how exactly does this connect with query processing? It was just a bunch of module theory. Well, here's the thing. Union is just plus, right? So we're dealing with polyset semantics, so we can just add things together, and that's the union. Difference, that's just negation, right? So we can just, well, it's a module, so we can just negate elements, and that's, if we want to remove something, we just take the negative and add that. And well, okay, we might go into the negative, but we can do normalization if we really want to. We don't have to do it all the time. Like in the relational algebra semantics, you're essentially doing normalization at every step, right? So you never go negative. You have to always make sure that there's no negative multiplicity. But in the multiset, polyset version, we can go temporarily into the negative, but that's not a problem. And we can insert normalizations if we want, and we cannot do it depending on like what's needed and what's efficient. So products is bilinear because we're using tensor products to represent products. Like if we have a record of several different attributes, then we would use a tensor product to combine them. And this is also the structure that we're using for computing joins. And then a lot of aggregation is actually linear. Like if we want to compute sums, we can basically project out data that we don't care about, and then we end up with a scalar, and that is the count. Well, that is the sum. We can do counts, we can do filtering, and so on, various operations. If we want to do things like max and min, then that is possible too, but we have to then work with semi-modules and semi-rings. But the entire theory works quite fine in that case as well. Then that just means you can remove elements, but sort of negation is orthogonal to the rest of the theory, so we can sort of add it or remove it as needed to do what we want. Right, so let's look at joins. Right, so what is, I guess I should have written the type of a join, but essentially we have we have two polysets and then like a tensor product of polysets, and then we want to produce another polyset. So think about it this way: we have a polyset of B's. So that's like the record data that we have. Probably a number of components of different types, and then we have some F, which picks out the attributes that we're interested in. So A is some kind of it might be a single attribute, or it might be a product of attributes. Like if we're joining on, like in traditional SQL, if we're joining on multiple fields, then in this case, A would be some kind of compound type. But F picks out the key that we're joining on. And so this index function, it takes the polyset and then it produces a coproduct over that polyset. So basically, we can think of coproducts as indexed modules, in this case, in an indexed table. And this works beautifully with the interpretation of coproducts as tries, and these representation theorems that we get from the natural isomorphisms. So basically, we think of coproducts in this case as just indices via efficient trie representations. And this is kind of a specification of what it looks like, which is just injection. Right? And then on the other hand, if we have an index, we can flatten. So we could just say, forget that we have an index, and then this works for any module, by the way, not just polysets, but we're going to use it in the case of polysets. We just throw away like case analysis and forget the index of this I should be an A. And then here is the interesting one. So given two such indexed modules, indexed by the same attributes, we can do a merge, and then what we get is the intersection. Right, so this element is going to consist of the intersection of the attributes in the elements of the input, and then as for values, we combine them, so we get a product of the values like this. So all in all, this can be combined into a join function. So I write the join as a join of two functions, because like that's the data we need. Like that's F and G picks out the attributes that we're actually computing on. So, I mean, it is a join of the two tables. It's just that the functions sort of carry that information implicitly, right? And it simply happens by indexing using each function and then merging them together, and then finally flattening. Of course, I mean, so the flattening is done because that's how join works. Like we want a table back as a result, but if this is part of a larger query that we're processing, then we might not want to flatten immediately. We might want to keep the index for later, and that's actually going to be important for more complicated joins. Right, so how does this merge function look like? Well, so the thing is, it works on coproducts, and coproducts have coproducts kind of work differently for each type. Or rather, we can analyze this index type of the coproduct to determine what it looks like, right? So remember that we have these natural isomorphisms. Let's talk about, well, what happens if the set is a sum? What happens if it's a product? And then, well, the merge functions for sums and products, well, it's just going to be essentially apply the isomorphism, merge recursively in each component, and then apply the inverse isomorphism to patch back up. And this general pattern works for, I mean, we might need some factorial action and so on for scaffolding, but generally it's just like unpack, merge, pack. And then in the base case, like the integers, we're going to have some kind of efficient int merging using radix sort or whatever linear time merge algorithm for integers that we want to use. And efficiency-wise, well, so suppose that int merge actually does run in linear time, which again, radix sort and so on can do. Then merge as a whole runs in linear time. And moreover, the output is actually linear, can be represented using linear space, because we're just using these symbolic tensor products, so we're not multiplying anything out. Even in the result, like in the final result, you might want to enumerate, but you can still do it at linear space because you're just streaming the tuples. Okay, so finally, let me show how this can be generalized to three-way joins. So bear with me if this is a little unreadable, but basically to write it compactly, we would just define this infix operator, which is just, well, it's more or less like functorial mapping. And then, well, suppose we have we want to merge three different tables and three different attributes. So think about like X has attribute 1 and 2, Y has 1 and 3, and Z has 2 and 3. Right, so it's kind of a cyclic three-way join. Well, what we do is just, well, merge in the first one, and then map over the result and merge in the second one, map over the result, merge in the third one, and then just combine the results into a triple. And I mean, the sort of the details to be fleshed out, but essentially this can be written down as a Haskell program that is about as long as this, like it's like 3 or 4 lines of combining higher order functions, and this is basically the algorithm that solves this problem in 4 seconds that took MySQL almost 2 hours. It's that simple. So if the input is size n, this runs in n square root n. In general, it's what is known as worst case optimal, which is so suppose that the 3 inputs have different sizes, and it's a bit more complicated to state like what is a good runtime, but there are definitions for this called worst case optimality, and this algorithm satisfies that. And also in practice, it runs quite fast. Right, so what did we do? Well, we developed linear algebra, module theory, but actually we started out with linear algebra, then it became module theory, and actually now it's sort of turning into general additive categories. It's a very general framework, actually. But it turns out even in this general framework, we can do databases and query processing. We get like just using these natural isomorphisms and abstract ideas, we get efficient data representations, we get efficient join algorithms. And so therefore I submit to you linear algebra as a query processing language. Like it's a nice way to write down queries. I mean, I would say just at least as good as SQL for as far as it applies. We get things that are nice, functorial and natural. We get efficient symbolic representations, tensor products, scalar multiplications, and we get very efficient joins. And well, that's it.
I think we can't hear you, Max.
Okay. That better?
That's better.
There we go. Sorry about that. Thank you, Mikkel. So please continue asking questions on the Zulip. We have a few already. First, Ohad and a few people agree with this question. There was some confusion about the unary coproduct, that maybe it was a typo. Because
unary coproduct.
Yes. That it, was it supposed to be? It said the when you had this page that the unary coproduct was the ring K, but should it be V?
Oh right, yeah. It should say V here.
Okay.
Yes.
Yeah. Okay. Great. And Manuel asks, how can one canonicalize the tensor product? There is usually no normal form, I believe.
Right. So yes. So if you have the tensor product over two like generic modules and you don't know anything about them, then you can't really compute the canonical form. You can only actually do it if you have knowledge that the modules are free modules, for instance. Which is kind of, well, that's like part of the point is that by taking this general approach, instead of saying that like if you're doing linear algebra, for instance, you might say, well, insist that everything has a base, and then, well, that means that we can define the tensor product as only on free spaces, and then and do canonicalization and so on. But yeah, it's actually an important point that we're defining the tensor product in general, with no assumption about the spaces, and therefore we don't want to do canonicalization, and we can't do it.
Yeah. Okay. So Kim Yo asks, you begin the talk with an impressive result where module theory trumps MySQL in the case of a triangle query. But what about the other way around? Are there cases where the module theory turns out worse than SQL? Or do you have some kind of result that the module theory always beats the relational algebra?
Interesting. So I don't think I have yet. I think I've yet to encounter any specific case where I was like, with module theory just simply can't solve. Because the thing is, you can always just, you can always just use the, like you're dealing with polysets, right? So you can always just deal with it using this mapping out principle, and just use like any function. I mean, you can plug in any function here, so it's kind of cheating a bit.
I think it's not an expressivity question, but more of a efficiency question.
Right. Well, but the thing is that, well, module theory in itself doesn't really have like a complexity.
Right.
I mean, it's kind of. I mean, so this particular, like, I mean, think of it as a theory, and the specific Haskell implementation is like a model of the theory. So I mean, to me, it doesn't really make sense to say that this theory is faster than the other theory. It's more that I think it lends itself to more efficient implementations more naturally. At least that's my. I mean, I don't think we've kind of got to the bottom of it yet. So I mean, kind of the jury's still out on this, I think. But so far, I think it looks like we're winning out.
Okay. And then Sam Lindley had a question. Would you like to ask that?
Yeah, so that's really following on from Kimi's question. I started by asking, well, have you carried out an empirical evaluation? Then I realized, obviously, you have done some. I was wondering if you could tell us a bit more about that. And I'm really interested in there's a kind of follow up from Pierre Marie as well. Should database implementers be using your theory as the basis for their engines rather than SQL? And do you have any evidence for that in terms of the actual and experimental results as well as the theoretical results?
So here's the thing that I think that the module theory is incredibly and the category theory in particular is incredibly useful for like developing these concepts and like deriving these efficient data structures and algorithms. But the thing is that once you have derived them, you can kind of backport them to the old systems, right? I mean, so this join algorithm, you can implement it. You can sort of lose the module theory and still implement. Implement like the functionality of it to get efficient joins. So I think it's more akin to like how every old object-oriented language is getting lambdas because they're sort of backporting functional programming features. Kind of the same thing, I think.
So I mean, do you have any plans to do that or to help database developers to do that, or are you just going to hope that they will see your work and steal it?
So we're trying to get published in a more sort of database-oriented place to actually sort of get more in contact with these people because, we haven't really had much success yet, like convincing actual database people that this is.
Yeah, I mean, might I suggest that the way that you might convince them would be to build a larger scale experiment?
Right.
See, look, I can actually run this on my real database I care about, and it makes it go much faster. Then they'll listen.
I see Fritz has a comment. Fritz, do you want to unmute yourself and?
Yeah, just complementing what Mikkel said, it's the case that during the study of so-called worst-case optimal query evaluation, that the classical approach, which is the system R approach, which has streams of records as the intermediate data structures, and query optimization you learn in database systems, is inherently, I mean, this is proved to be, so it's inherently incapable of expressing a solution that runs in less than quadratic time for triangle queries. In general, the class of queries, it's called cyclic queries, is very hard for database systems. They tend to have special rules or special code that they dispatch to, because they're using flat records that corresponds to multiplying out the tensor product. While here it's being kept in a lazy data structure, and if you have a morphism, right, you know, if a tensor product of two things, you can just apply it, you know. Computing cardinality is a simple case. So that's why I would argue that even if you take indexing into account, so which means, because that's not part of relational algebra, so as Mikkel said, you know, there's relational algebra at the computational model. I mean, so let's add indexing in there. Those can be expressed in you know, as mentioned, in asymptotically worst case linear time. So that would indicate that, you know, at least asymptotically, the standard implementation techniques can be emulated in this fashion, at least, and in some cases beaten, because there's more data structures than just flat streams, you know, lists of records.
Great.
Thanks.
And I may just ask, I've been in touch with a number of database people, and they basically, I completely agree, we've worked on that and we'll be working on that, but it's a very strange model to them. So the idea of having you know, kind of other data types than that is not entirely new. There is so-called factorized databases, which are parts of, you know, they basically have symbolic Cartesian products. But otherwise, you know, most of the regime follows streams of flat records, so that if you have a Cartesian product or a join, it gets multiplied out into a huge intermediate stream of you know, in the worst case, the Cartesian product becomes quadratically bigger than the input. In our case, it's just as big as the input, it's just a pair.